Okay. Let's share the whiteboard. Oops. So roughly speaking, we have two area, which is not exactly separated, right? Actually, we study more classical physics. Even in classical physics, we also study electron. You see, we study electron first in classical physics, right? Because this electron is a negatively charged, right? So this final thing, but before we go, so how should I start? So we started from starting the ball. How to describe the ball if the ball is moving? Oops. If ball is moving, so we can use position, right? To describe their position, which is time. Okay. This, and also this is used. Oh, you have done chemistry, math already. Then we talk about velocity, right? And acceleration. But in high school, acceleration is constant, all right? So that is the basic, when we describe how ball move, we just use these three ideas. So from this one, we can generate the formula. The final velocity is equal to initial velocity plus acceleration multiply the time. Okay? And also we know that the displacement, we use S, is equal to initial time multiply T. Okay, so we can apply this formula to solve the problem afterwards. Right? T squared. Okay. In addition, there's a V squared minus U squared equal to 2SA, all right, or 2AS, doesn't matter, all right, 2AS. Oh, sorry, this is, we just use A here, F acceleration. So in this case, we call this, when we describe that with the mass, we all call this as particle, can you see? So these are called a particle. Particle has mass, can you see? Particle has velocity, and also particle also have momentum, right? Do you remember this momentum? And of course, momentum is a vector. And also particle has kinetic energy, including electron, you see? That is another very useful formula is, as the particle has a formula, so this here, mv squared, okay? And eventually you will see the potential energy is useful, right? When you start to if that is near the ground, the gravitational potential energy can also written as form. Okay. Now all of this formula is based on Newton's second law, which is very important. You see, so Newton has the three laws. Newton's three law. That is why Newton's law can be used to describe many things. Okay, so Newton's three law in physics. The second law is most important. The net force is equal to the mass multiplied acceleration. So if we know acceleration, we can solve any problem. Okay, and at the beginning we started the object fall. Can you see? We start object falling down. Can you see? Above the ground. Can you see? So that's how the gravitation is G. And also we starting the object moving in along the straight line, right? And if we know the force, that's another thing. Newton tell us if we know the force, then we can accelerate, we can work out the acceleration, you see? And also, yeah. 你走过来点，你看你走过来不会进。哦呦，你把门关一下。这个门，我这个地方很小，就 Okay. Oh, you got note of this formula. So this is Newton's law, all right? So over just so, but I tell you what, sometimes you need to rewrite this equation. Okay, for example, acceleration can be written as F divided by m, right?
When do you have to use vertical and horizontal? I don't know.
Yes, if you want to start in the motion, this is just one dimension. This is one dimension, okay? One dimension is 0. You can use this formula. However, if you use a circular motion, so that's things getting complicated. If you consider this motion around the circular motion, right? Then you have to use this formula, which is so for example, this is this object M, right? And if they have to consider this so-called the centripetal acceleration. I use a red color. You see? So this is very useful formula when you describe the circular motion. Do you remember the circular motion? So this is so another formula for acceleration right down here. AC is equal to v squared divided by r. Can you find this formula? That is kinetic physics.
Yeah.
Yeah. Okay. That is one. We'll go to there now. Okay. Now, if the velocity is this is the velocity. Okay. For the circular motion, you have the period. Can you see the period is I just write that here.
Time divided by number of revolutions.
Yeah. So the return another two formulas. So velocity can be written as the distance of one circle. Can you see this is circumference one distance divided by the t. Okay. And the t can also be written as a number of turn divided by the total time. You see? You see?
Time divided by number of revolutions.
So number of revolution or other way around. You are just very wrong. Can you see? Can we say number of revolution? Okay. So can we just use a number of revolution divided by time? Okay. That is an additional formula. Now actually,
can I pause out?
Yep, I got the pen. You want to read the color? 那写错了，好不好？你就看我这个，你看我反正帮你 cover 掉就行了，好不好？因为我这些都讲完了，看见没有？都讲完了。那么这个是还有一个就是，let's just speak English.
Speak English. Horizontal and vertical.
Yeah, that's another. Yeah, we'll talk about that.
Okay.
This is too crowded. This is the basics.
What's one dimension?
This in space, our space is 3 dimension. If on the plane is 2 dimension, if it just moving along this gap is 1 dimension.
Okay.
How many variable can be used is the determined number of dimension. Okay. So here I just use x. All right.
Yeah.
And this is circular motion. Now, Newton, according to Newton has also worked out the force. Can you see? I put the force here. So they have many force formula. You have to remember. You have to know how to use it. One important force is gravity. Can you see? Universal gravitational force. Can you see?
Okay.
That is R is a circle. Can you see that? That is distance between the two objects. See? Okay. Yes, that's Newton's law. One is m, another is capital M. So the distance is R. Can you see? And the force is attraction all the time. Okay. All the time. So that's one force. Another force is regarding the charge. So I write this force over here. Can you see? So why do we know force? Because once we know force, we can work out acceleration, remember, all right? Because we need to know the acceleration. In this formula, we have to ask what's the acceleration. But sometimes acceleration given to you. The Coulomb force is similar to the Newton's law, but they use charge. Can you see? Q1, Q2 divided by R squared. You see? So that is a 2 charge. Yeah. Yeah. The K, that's right. In your formula, K can be rewritten as this form.
Yeah, but that can
you don't have to
be represented as a constant.
You don't have to. You just know they are equal. Okay.
Okay. Yeah.
And at the moment, the wave is not start. Can we put the wave other? Start the wave otherwhere? Can you put the wave elsewhere? Okay. Wave elsewhere. So we are still the particle. All of this is a particle. Can you see? Okay, all of these were still the particle. Even coordinate ray, you can consider the particle. Can you see? You see, include electron. Okay. Okay. So can we another force is the Lorentz force? Can you see? Gravitational Lorentz force that is determined. Can we put the? I don't have put. Can I put? I just put Lorentz force. You know that is QVB. Can you find this formula for me?
Yeah, it's right.
Lorentz force. Yes, that's called Lorentz force. Next page we'll discuss how do we use it. Okay.
Is this one for like force between two charges?
Yes,
Okay.
that's right.
And
but
this
Lorentz force is a force inside the field. We're talking to how
okay.
we put all these forces together. Can you see?
Yeah.
Because we'll count how many forces. Apart from the force, sometimes you have to start. They don't ask you, but sometimes you have used normal directional force, right? And sometimes they also ask you friction, although you don't have to know them. You see, this is called friction force, dragon force.
I think we have to know how to draw vector diagrams for
That's right. And also T for tension, can you see?
And also pulley.
Yeah, pulling force, T for tension, can you see? Not the capital. T for tension force.
Yeah.
So that is anything else we're missing? Another force formula in electromagnetism is called the length, okay? L multiply I divided by multiply B multiply sine theta.
The formula sheet is like B.
Doesn't matter. Order doesn't matter. So in algebra, A multiply.
I know, but I think that's how we memorize it.
Well, because
doesn't matter. I know.
Okay. So that's electromagnetism. So traditionally, so this area is called electric charge and field. You see, two ideas: charge and field. Because you have to know. We'll talk about this later. Charge field include electric field and magnetic field. Okay. Now for the light ray, in Newton's time, we still consider light travel along the straight line. You see, if you have mirror here, can you see? Have you started snail?
Yeah.
Yes, that's right. So light is we got n1 sine theta 1 equal to n2 theta 2. You see, we'll talk about how to use them after. Okay, so this light, in this case, light is treated as the particle. Okay, yeah, that's right. Okay, this is very brief summary. Okay, now in terms of the wave, we have studied say how do we generate a wave, because the vibration will generate a wave. So basically, when we describe the wave, we study transverse wave all the time. Transverse wave can be drawn easily. Another way is called longitudinal. Longitudinal wave can hardly draw, right? So this is how do we describe the wave. You see, you can use a sine function to describe the wave. And remember, this wave move, all right? This wave move at velocity called wave speed, right? So wave speed and also the peak to peak distance, can you see? This I just draw this wavelength. Yeah. This peak to this. We often call this peak to peak distance as wavelength. Okay. This wavelength is very important. When we study quantum, we have to use wavelength. Okay. And also remember these waves move at a certain velocity, and this velocity can be simply written as lambda multiply the frequency. So that is the formula we have to use in both kinetic and modern physics. Okay. Of course, things getting complicated if you want to do some. One thing is a wave travel. So you have to remember, next moment, the wave will move. Can you see? This wave will move forward. Can you see? So the wave is moving. You agree? Yeah, the wave is traveling. Okay, I don't want hard to draw. That's it. That is
also like when it travels.
Sorry.
Does it also like when it travels?
Yeah, they actually, if you want to study wave, you have to study the vibration first, you see.
Like, does it go like up and down?
Yeah, so if you, for example, if I just consider the oscillation, can you see, you just, have you studied this spring on the ball?
Yeah.
It will all up and down, can you see? So in this case, if the mass is m, and if this x-axis is y, is 0, and the formula can be simply written as a multiply sine, you can see cosine as well, multiply omega. Do you use omega t? Have you studied this formula? Do you know omega now? Sometimes they don't use this omega. Oscillation, did they say to start oscillation?
Oh, I think we did.
No, probably they didn't. Yeah,
It's not in the
yeah,
syllabus.
it's not. You don't start oscillation. Okay, doesn't matter. In mathematics, you study the how to use sign modeling, sign
Okay,
function
I don't
model.
think we
Okay,
need to know that. Can we move
but
on?
yeah, let's move on here. So but don't. This is vibration. Okay.
Yeah.
If you know the web, because every point is vibrate. Can you
Yeah.
see? It's important. This is oscillation. Okay. So in this case, we have moved to the standing wave. You see, when we describe the standing wave, for example, if you fix a string like a violin, okay, you plug that violin, then you can generate a standing wave. Okay, so the standing wave is such you can use a standing wave. So you can in this case, this is called a fundamental. You see, this is a fundamental. And you go to next one. If you go to next one, and the high frequency will show up. Can you see? So if you high frequency, if you plug that the string harder, you can obtain this wave. Can you see? This is also a standing wave. Can you see? So in this standing wave, you need to know the formula. If this distance L, if there's a distance between the two standing wave, then you have to know this formula. You'll be able to work out this because it's half wave. Can you see? The total this is total half. So therefore, the length the L is equal to half wave. Can you see?
Okay.
Half wavelength. Okay. This because this is the first harmonic. We put the sub one here. Did you put a sub one? You don't.
Wave. This one?
Yeah, this harmonic. Yeah, n, that's n, that is n. Okay. So in this case, however, this will hold just exactly one wavelength. You see? So this is just one wavelength. So that is so therefore that will take it one, that two. Can you see that equal to one wavelength? So what you need to remember is that if that this is a formula for the for this case, two end is fixed. Can you see? So if I highlight this called the node, can you see? This is node. Node is not moving. Can you see? The node is fixed. And inside at the center is called empty node. Okay. So that is how to use this formula. So therefore, if you use this formula, so basically if you rewrite the second formula, can you see? If you rewrite the second formula, we can say it's double of half wavelength.
What's n in this case?
Yes, I will show you. So this is n equal to 1. This n, that is the order of harmonic. You see?
Oh.
When n equal to 1 is called the fundamental. That's a
wait, so we can write the first one as 1.
Yeah, first one, yeah. I will use this formula, can you see? After you put these two formula together, we know that when n equal to 2, the general relation is n multiply half wavelengths. I put n here.
Yeah. Okay.
So that is the formula. That is the formula, okay. So what is n? So n equal to from 1, 2, and go higher, can you see? In integer. Now, this time, it's important to know how to apply this formula here, because sometimes they will ask you not the wavelength, but the frequency.
Yeah.
So how do we know frequency? So
rearrange
we rearrange this lambda in terms of frequency. Can you see that? So if we rearrange lambda as a frequency, so this formula can be derived as the frequency. Yeah. So can we just write the formula for so that I copy the formula. They didn't tell you formula.
What do you mean? This formula?
Oh, you have to know how to combine these two formula, all right?
And C
because you can also, of course, the lambda. I give you one formula is useful. So this if you solve this lambda here, okay, lambda will from this formula. Lambda, what is lambda? Lambda is equal to V divided by frequency. You see. Okay. So if you combine these two formula, you should be able to work out for the frequency.
Oh, okay, yeah.
Okay. We'll talk about how to use them. Okay, that is all about the classical physics. Okay, and also thermal. You don't start thermal this time.
No, it's unit 1 and 2, so it's only unit 3. These.
Yeah. Okay.
Topics.
Okay. Also, no thermal, no Ohm law, right? No Ohm law. Okay. Okay. Okay, we got everything. Another thing we have to talk about how to describe magnetic field. Okay. Oh. Now, things getting complicated when we study the electron in the atom. So this is electron. When we study electron in the atom, we have trouble. So I draw the diagram here. So when we study the hydrogen atom, we know that electron is not electrons inside. So electron is here. I use this blue. This electron. Can you see?
Hydrogen only has one electron.
Yeah, one electron. So it's taken a long time. We just cut the story short. We know this Bohr model. Can you see? Do you know this Bohr model of atom? Okay. And these also have n. So this n equal to 1. You have in chemistry, you know that, right? The first shell, the n equal to 2. And this distance called Bohr model. So Bohr model says is Rn is equal to a constant multiplied n squared. Do you know this formula? Bohr model? No? Now you don't need this. You don't need to do Bohr model. Okay. So I just write down here. But more importantly, I write down the energy formula here. They didn't tell you. They didn't tell you energy formula. Hydrogen formula, energy formula. They should tell you. No, not like this one. Yeah, I have to write down here because it's important. Even in chemistry, you need to know this formula. All right. So energy formula is equal to. Have you seen this one? 13.6 eV. Have you seen this formula before?
No.
I just put it down here. It's just a constant. Can you see?
Oh.
RHC. That makes sense now. RHC divided by n squared. So that is energy formula. And R is this one. Rydberg. R is Rydberg. R for Rydberg. It's German. Because
this formula is used to determine energy.
Oh level. Yes. It will start the. I can put the second formula here. So this formula. So if you are here before we're talking about this formula afterward. Okay. So this is we know that this is hydrogen is proton. You see, is electron is negative, and they have force attraction force. Do you agree?
Yeah.
That's obeys the Coulomb's law. So that
orbits around the proton.
Yeah, orbit proton like a circular motion. Okay. Now before that, we probably have to tell you that the Kepler's law. Can you see? If this consider this as a star, okay, we can do another circular motion. So Newton has very clever. Newton have done a lot of things in physics. So if I just draw, according to Kepler, the orbit of the planet is ellipse, right?
Yeah.
But
we need to know these 3 laws.
Yeah, 3 laws here. Kepler have 3 laws here. So first law is that you say if this is our sun, can you see? We put the sun at this one of folks. Can you see? This is our sun. And then the planet will be like here, can you see? So mass of sun. So according to Kepler's law, that is the first law. So orbit the ellipse about the sun.
And the second one is equal time,
equal area, equal time, equal area distance. So that what that means that if I draw a different color. So if I just connect them, so that's the distance, can you see? And that if you count the same time to see how the planet move, you will find that equal time at given equal time, these areas are identical. That kept the second law. Can you see?
What kind of questions will they ask?
They will just ask you stay. How to what is Kepler second law?
Okay.
So you will say,
well, no calculation.
Yeah, no calculation, no calculation. That's its law. So basically, in this case, these areas are identical. However, Newton in high school we don't use ellipse because too complicated. So in physics we study this. We study the Kepler third law by assuming it is a circle. Okay. For example, this R1. Okay, this R2. Okay. In this case, you consider two planets. So this sun is still at the center. Sun is still at the center. Okay. Okay, but by combining Newton, Kepler's law, we can prove that law. So Kepler, this second law, can you see? Can you write down here? This Kepler's first and second law. Okay. The third law, this is Kepler's third law. Okay, this is the third law. The third law says that the r, can you see the distance r cubic, r. Sorry, q period square. Period square divided by r cube is constant. Okay. This I write the different form for you. Can you see? This is T1 R1. That is a T2 square and R2 cube. Because this represents the first planet. This is the second planet. Can you see?
And that links with the
second
one, the second law.
No. They have nothing to. They are independent. They are three laws independent.
This one's assuming that's a circle.
If they are identical, then you don't have three laws. You need two laws. So remember, they got Newton. You know how the three laws, okay? And so that is all about. Can you see any other formula we're missing? That is induction. We'll talk about induction later. Can you see? It's a bit crowded here. So you got electrical field. I just put it here. You got electrical field here. You got magnetic field, and they are not. You can induce. Can you see? The voltage can be induced. Let's put Faraday's law here. Yeah. No, by changing the flux. By changing the flux. The rate of change, we can.
The flux of B or the flux of E?
Flux of B, yeah.
Okay,
we don't. Although there are, you can talk about flux of E, but we only study the flux of B. Can you see? If necessary, put B here. Okay.
Yeah.
Just remind you, it's B.
Yeah. So B doesn't move, right?
We don't study that.
Yeah.
We don't use the idea. In university. You will study that. That equal to B multiplies area and multiply the angle between these two. Can you see?
Okay.
Cosine theta. So that is induction. Okay. Faraday's induction. No. Yes, that's right. We got to this formula. They talk about EMF. So this called EMF, motive force.
Okay. Wait, it's because in chemistry we study electromotive force. So the E node.
Well, in chemistry we study. We also use the voltage. Yeah, that's right. They sometimes use a different notation. It's okay. They use E, right? Okay, we got everything now. Okay, now by the time we start go to inside the nuclear, do you remember? Then we have to consider another force. You see, although this force is invisible, it's not. It's different. For example, consider the nucleus of the helium, right? We have two protons inside. You see. So yeah, that's right. Because there's the force, because of Coulomb's law, we can hardly, because you have a strong attraction to hold them together. This is a helium nucleus. It's a helium nucleus. Okay. Do you remember? I just knocked down the electron, so that's a helium nucleus. So the attraction is called a strong interaction. You see,
strong.
So this attractive force called a strong interaction.
Yeah,
it's called
it's one of the fundamental.
Yeah, one of four.
forces.
Yeah, they call strong force or strong force, strong interaction. Okay. Okay. So that is something new. This, as a whole, this nuclear.
This is using standard models.
Not yet, not standard model, not yet. So basically, this nuclear, you can see. So this is nuclear. So everything I draw here is called nucleus. Nucleus.
E-U-S.
Yeah, nucleus. So this is atom. You can see this hydrogen atom. Okay. You were studying you were, is that involves nuclear physics this time? Nuclear decay, right? Where's nuclear
decay won't be.
Wouldn't be.
Yeah,
Oh, not
here,
oh, okay.
Because it's part of unit 2.
Oh, okay.
Half-life.
We don't study that
No,
part. No, okay, that's good. That's good. Okay, that's enough. That's for induction. But during the time, we have trouble. Can you see? So that is in modern physics, starting with 2 experiments. I write down here. So modern physics start from 2 experiments. One is black body radiation. Okay, black body. Just the name, black body radiation. So radiation is, according to classical physics, is just electromagnetic wave. You see?
The energy of the wave.
Yeah, the wave is radiation. So when we started black body radiation, we use the EMF wave. You see, we first electromagnetic wave. You see.
Yeah.
Also, that represents light or radiation. Okay, that is how we use. How do we describe radiation? At the beginning, we use the wave. You see.
So
and
yeah,
but this model is wrong. Can you see? You cannot use this model. The correct model is a Planck's constant. Yeah, this is a photon. The photon, can put a pH here, is equal to the constant multiply the frequency. Okay. And in addition, you can
the formula will be used a lot, I think.
Yes. We can. I told you you have used this formula.
Yeah.
Because in this case, because this particular formula, the wave formula, this formula, can you see? In the case for the photon, can you see right down here? For this electromagnetic wave, you see this wave, we have C equal to lambda multiply frequency. Okay. Also, it can written as lambda divided by T. Do you agree?
What's T? Period.
T is the period. Yes. You see, because the frequency can be written as 1 over T. You see.
What's the unit for T in this case?
Second.
Second?
Yeah.
Well, don't you use days in the
no, we in international, we're talking about in the international
SI
system.
Unit,
Yeah,
but like
SI.
when calculating using Kepler's law, is it days?
No, they will tell you. I prefer is second.
Oh, okay.
Okay. Unless they say day, you can convert that into day afterward. Okay. You see, we cannot use more than 1 unit.
Yeah.
Okay.
But okay. But if they give you days.
Say year. If it's year, you use year for both T.
Okay. But you can't use different ones. Yeah.
You cannot use different unit to solve problems.
Yeah, it has to be consistent.
Okay. So these particles. So these particles is very strange. Can you from here? So I have to highlight that one. From this time, we realize these particles are not necessary particles. So all of them, can they? Yeah. Unless electron is free, can you see? So these things are called these sometimes behave like the wave, you see. So these are particles, you see. These are called the particle, you see. But the particle can also, this starts from here, okay? So this is photon. Why the photon is introduced? Because this is wrong. So in this case, we cannot use electromagnetic wave. Okay. Can you follow me?
Yeah.
So that is why we use the photon as energy. So this applies the photon. So when we use the photon energy, can you see this photon electric effect now? We can transfer the photon energy into the electron. You see, electron have this energy, and they can escape from surface.
Okay.
So this is very important. It's called the photon electrical effect. Okay. Yeah, photon. They can still down. They call the photon electric effect. Electric effect. Very important experiment.
So like
okay.
boom, boom.
So this means that energy. So basically, if the energy is transferred to the kinetic energy, and yeah, that's right. And in this case, the EK can also written as the E multiply the stop voltage. Do you know this formula?
Oh no.
No?
Yeah, we do know what EV is.
Yeah, have you studied this part?
Well, you can also use that for it.
No. When you start photon electric effect, we must know this idea. Unless it's not required. I think it's not required.
But I think assumed maybe they.
Yeah, then in that case, I will not mention the stop voltage, all right?
Too much information already.
Too much information, okay? Now, but when you start a photon electric effect, you have to understand this diagram, which is very important, okay?
Okay.
So this diagram says that the straight line, they have the negative y-interception, can you see? The y-intercept is negative. Have you seen this diagram before?
Yeah. Okay. The y-x intercept is the threshold frequency.
No, that is work function. Yes. Okay. So I draw this straight line here. So basically, this vertical represent. Oh, I changed the color. This vertical represent the electron kinetic energy. All right. And this x-axis represent the frequency. All right. And this is a threshold frequency. You see, or you can call cutoff frequency. That's a minimum. And this is a negative work function. You see, this y-intercept is negative function. In other words, if the frequency is too low, then there is no photon electron.
If it's too high, then there's no photon electron.
No, if frequency is high, you always get photon. If the electron, so this part, so when frequency is larger than this threshold energy, you can always get electron come out with certain kinetic energy.
Oh, that's the type of question when they ask you to identify like which type of material.
Yes, they give you material 1, material 2. They have different work function.
And then the graph you have
then the cutoff frequency will be changed, will be different.
What's cutoff?
This is threshold function.
Oh. So like for those type of questions, you calculate the y-intercept.
Let's talk application afterward. Okay. We have to summarize everything you need to know first. Okay. Another thing is we can use the photon to connect with electron inside the atom. Okay. In that case, the electron will change. You see, they will change their energy. You see? So what is the delta E? Then we need to draw this diagram now. Can you see? This formula tells us, so basically, if I draw this energy first, if you have energy diagram here for the hydrogen atom, okay? If you just plot this energy diagram, this formula here, and this is so this is the ground state, lowest energy, can you see? Second, third. Have you seen this diagram before? This is how to, based on this formula, we can draw that formula, can you see? So this level, energy level, it's called energy level, they call energy level, okay? Like with different story.
Orbitals.
You can see the orbit, but not necessary. This n equal to 1. Do you agree? The n equal to 2, n equal to 3. Can you follow me?
Yeah.
And n equal to 4, getting crowded. Okay. And when n equal to 5.
H with less energy required.
No, the interval decrease.
Okay.
So finally, that is n approach to infinity. Can you see?
And the electron's free.
So what happens if the electron normally stay at the bottom? Can you see? When they catch up the energy, they will jump. Okay, I just make this
excited.
Yeah,
Yay.
because excited. They catch up something. They'll just go up. Can you see? Go up. They can go higher if they got more energy. Can you see? So electron can jump from here to here. Okay.
So if you shine like a ray of light onto your material, the electrons will jump.
Yes, depending on the frequency.
Okay.
So in this case, in this particular case, the photon energy here is equal to the energy difference. Can you see? In this particular case, photon energy is equal to the energy between the higher energy, that is E2, higher energy, take the initial energy. Can you see?
Okay.
So this is a special case of this formula. Now return to this guy's formula. Okay. Yeah, how can it? But this formula was used before the Bohr model. The Bohr model. So how did he know that? He's very clever. Okay. He said that.
What's the model before Bohr's?
Oh, there are many models. There are plum pudding model, yeah, Rutherford's model.
Oh, yeah. Rutherford. Okay. Yeah. One question they will ask is to compare Bohr's and Rutherford. Sorry, I went off track. No,
we don't. We focus on this first. Okay. There's too many things. Yeah. You spend 1 year to study. How can we talk about everything?
Okay, moving on.
Now, this is very important. Watch carefully. Okay. If I rewrite this one in terms of the second formula, okay, what is the second formula for the photon? Can you see this formula? This one formula for if you see this formula. Okay, if I just rewrite this part, can you see? Become HC. What is C?
Speed of light.
Yeah, nice speed. So that will become this energy. Can you see?
Wow. Okay.
I use this formula here. So basically, yeah. So that will become R HC. I use this formula now. Energy level divided by N. I use the one, you know, it's called the final. Can you see? It's called the final square. Can you see? Take energy, which is negative, right? That is R. What's R? Readable constant. Right. No. R is readable constant called.
And H is Planck's
Planck constant. Oh. So HC, can you see? Divided by N initial square. Can you see?
Oh, okay. So this is another way.
So that is come from this formula. Can you see? That use photon idea. I can write down here. So that equal to the 2 is equal to the final. Take the initial. Can you see? Okay. So if you use these formulas, we can obtain this old formula, which was discovered by Rydberg before this idea. Can we cancel this H on both sides? Can we see cancel H? Can we see both sides? Okay. Can you see that?
Yeah.
And then if you watch very carefully, so I put my icon elsewhere. So in this case, from this formula, we can obtain a very strange formula, which is R1 over lambda equal to R constant, Rydberg constant, divided by NF square, take N.
You factorize.
Yeah, you factorize. So that's called Rydberg's formula.
Okay.
This formula.
Yeah. And that's used to calculate.
There's a wavelength. You can count wavelengths. Okay.
Emitted.
Both emitted and a good question. Emitting and emitted will use the same formula. Okay. Okay. So basically, we just draw this I always draw the absorption band. Can you see? Absorption band is can we draw the the real stuff. So it's visible. Can you see? Starting from red and go to the origin in the rainbow, the order.
Yeah.
And after that is yellow. Can you see? That is visible spectrum. Yeah, spectrum. And that is after that got green. Can you see?
Wow.
Do you remember we did experiment use a sun ray in Shanghai? Do you remember?
No.
We use a glass. We just use a prism in your bedroom. Do you agree?
Optic.
Yeah. Oops. It's blue. Looks real. Can you see?
Yeah.
And then finally got purple. You see. Then after that we cannot see. All right. I just write it down here. So this is visible. This is called the visible region. Can you see? The visible light is visible light. And after that, it's called infrared. Do you know infrared? And that after that called UV, ultraviolet.
Yeah.
Okay. And then from here is this is a microwave, X-ray over here. Okay, the gamma wave over here. All right. This is microwave. And then they got radio. They got radio wave. Okay. Radio.
And wavelength increases?
Yes, good question. So in this case, the wavelength is increasing towards the right-hand side. So you can see that the wavelength is increasing. Okay.
And then shorter the frequency?
Yeah, that's the short frequency. So the frequency here, is increasing. In opposite, can you see?
Yeah.
Wavelengths go this way.
Yeah, because if it becomes more stretched out, the more less will pass.
Yeah, because it was this reciprocal. So now the absorption, good question. The absorption is dark band. Can you see? For example, what is absorption? Absorption is this dark band. Can you see? It's called absorption. Can you see? Some frequency is stolen. Okay.
Oh no!
Yeah, that some photon with this frequency was stolen by electron. Eaten. Can you see? You cannot eat other. You can only but they get more crowded. Can you see?
For different materials. Yeah.
No, this is for hydrogen.
Oh, for hydrogen only.
This is for hydrogen only.
Oh.
Because why? Hydrogen is the simplest atom.
Oh.
In high school, just study hydrogen atom.
Okay.
That's enough. Okay.
Yeah. One electron.
Yeah. There's no point to study every atom. Okay. So each of these can be represented. They will tell you, for example, if this, for example, wait a moment. If they will tell you if this lambda or this two, do it again. For example, this is if this is lambda, the tail number, can you see? For example, if this is 420, okay, nanometers. If that is the case, can you see? So what can you do with this wave number? You can use this formula to find the energy interval. Can you see?
Wow.
Okay, so this number can be used as this can see HC divided by this 420 nanometer. You have used international system, right?
Okay.
We multiply -9 here. Okay.
So meters.
Yeah.
Okay.
That will give you the energy level, the difference. I use this diagram. Can you see?
Yeah.
You can find the energy interval. Okay. Okay.
Wow. Okay. Take a break.
Well, no, let me just check. Oh, finally, I need to draw the diagram for you. Yeah, after that, we'll take a break. Okay. So this be careful. This is very important diagram. Okay. I only teach my students. I don't tell everybody.
Okay.
So when we study the quantum mechanics, another thing is relativity. We'll talk about, we write a formula here, okay? We have relativity here, so that is a time dilation. I write down here.
Also, The momentum one, what is that?
Okay, one moment. Yeah, I write down here. Time dilation and
relativistic
length contraction. Can you see?
Yeah.
Can you got these two formula here? That's relativity. So what is gamma? Gamma is Lorentz factor.
It's the
it's,
square root.
yeah, you have to know how to use this formula. Can you see? One take V over C.
Yeah.
Have squared in. Can you see?
Yeah.
That's enough. It's time dilation and time constraint.
Relativistic momentum.
Yeah, okay. Of course, we know this formula before.
Oh, the relativistic momentum is
momentum, you have to change the formula slightly. Too crowded. Okay, I don't want to write everything here. Okay. This pertains to this table. Okay.
Oh, sorry.
I will finish this table and we'll take a break. Okay. So basically, what we try to tell you is very important idea. How do I choose? Can I just draw it by hand? Okay. So basically, we have started the night before. Can you see? We have also started electron. Can you see?
Okay.
Electron. Okay. At the beginning, we know the light. This is the model we use. Can you see? This is right down here. This is called the real thing. Can you see? Real world, real object in the world. Can you see? Gravity is called the real stuff. Can you see? But this side called the ideal model. Okay? We use model all the time in physics. Remember, when we study physics, we never use real object. For example, if you study the car, we just reduce the car into the dot. Do you remember? Okay, we don't know. We don't pay attention to the size, the color. Yeah. When we study the light, at the beginning, so we use, I put down here, it's called ideal model. Okay, use ideal model. Ideal model. Okay. That looks better, okay? Okay, this is a very important moment. It's a summary of everything, wow. You see? Okay. Before this idea is so this idea is the modern one. That is the beginning of modern physics. I'm just trying to, okay. So this idea is happened in 1900, right? By Planck. Planck constant, Planck. However, so in that case, we use light ray, can you see? So, sorry, not sorry, it's confused. We use wave model, can you see? We use wave, so we use electromagnetic wave, right? Okay. Electromagnetic wave. That's before this time. 3D. So we use wave model to describe light. However, according to Planck and Einstein, this time we have used a particle model. You see, it's called photon. Okay. So maybe you have to redraw this one. It's yeah, but one moment. It's too much information for you. Doesn't matter. You can repeat it and watch this. All right. I still have to call this. So we have talked about ideal model. I put ideal model here. It's called ideal, not real. Okay, model is not real. It's approximately right. Okay, so one model is called wave model. You see. Okay. Now this wave is not any wave. It's just model wave, right? Okay. Model wave. Another is called a particle. Again, this particle is just a model. Okay. Particle.
So it's very successful. So light can either describe by the wave and the photon. Okay.
Yeah.
However, electron started always a particle. Can you see?
Yeah.
Electron is a particle. Do you agree? Electron is a part. They have the energy. Can you see? Electron is a particle model at the beginning.
It also behaves like a wave.
Yes, that's why. And this guy very clever called French, the Broad.
The brain.
The Broad. The Broad is very clever. He didn't study physics.
Oh.
He studied philosophy and
Oh.
history. He said, well, hang on.
What's the
You
humanities
guy missed this part. Can you see?
because it's common sense.
Yeah, it's common sense.
Can be,
so therefore, the whole thing that electron inside this one must be described by my wave. Okay, so that's the Broglie wavelength now. You see,
no one realized it
by
before
P.
him.
Okay, no one. He got Nobel Prize.
Wow.
He's very smart. He's very smart. Okay.
Okay.
He got Nobel Prize.
A philosophy.
So, question: what is P? How to write is a P?
MV.
P for momentum. Very good. Very good. Let's just highlight this formula.
But this time it's relativistic math.
Non-relativistic. Yeah, it's non-relativistic. Can you see? So here we use this formula in the quantum mechanics. Can you see? You see?
Oh.
So this table tell you everything. Okay. So both light and electron are real stuff. Okay. But in physics we all use model.
Yeah.
And in history we use light wave. It's a particle.
Yeah. And
then we jump to the electromagnetic wave. It's okay. We can see the wave like radio wave. Radiation is a wave.
Yeah.
But
we did the double split.
Double split. Yeah, they all behave like wave. When we have the black body radiation, we have trouble.
Yeah,
so that's why we have to use the photon particle model to describe light. Electron at the beginning, when J.J. Thomson discovered electron, it's just particle, right?
Yeah.
The particle can be used this formula. Can you see?
Okay.
However, when we build the Bohr model, we have trouble.
Okay.
We cannot use Newton's orbit.
Okay.
We have used this another formula here. The Bohr's. I put this. I replace this by Bohr's model. Okay. That will make this diagram more complete. Can you see? I replace this by his condition. So he said.
What was the formula before?
Yeah, one more. It's just the radius.
Right,
we don't use radius. So, but this is more important. This formula, just realize. He said the momentum, can you see? The momentum multiply R, so R multiply the momentum must equal to, very strange, equal to Planck constant multiply N divided by 2 pi. Check your formula.
Dun, dun, dun.
Yes, okay. Okay, not quite. Yeah. This one, can you see? But these two are identical. If you combine the Broglie's formula, I will show you next time. Okay. So I highlight all links together. So this is Bohr's condition. Okay. Bohr have this hypothesis. Can you see? Can you see? Of course, you can combine the Broglie's formula together. You can get another formula. From here to here, can you see? We just said this lambda equal to HP. You got they just sub to this formula.
Yeah.
That's all. Okay. Any questions? You see, we got everything. Can you see?
Really, yeah.
You show me.
I think I'm like familiar with.
Yeah, can you use this ding 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 ding? You see, so we start from Newton. Okay, Newton said why objects move, why the ball drop, it's called free fall. I didn't talk about projectile motion. That's projectile motion.
Yeah, projectile and incline motion all here.
Okay, we'll talk about projectile motion next time. Okay, probably tomorrow. All right. Let you digest. So, so Newton said, well, use my law. Can you see?
Yeah,
so Newton's law. This law can be solved. Everything fundamental law. Then you can, once you got acceleration, we can calculate this easy. Can you see?
You don't need to know time, velocity.
Or time is always changing.
Okay.
We can use the formula to predict what is the velocity at a different time. Yeah. For example, when we start motion, we need to know initially the velocity is 0. What will be the velocity when it touches the ground? So which formula shall we use?
Well, the horizontal or vertical?
No, the vertical, the free fall.
Yeah,
can you tell me if that's a fall, how much time is taken for this object to draw? Is height h the
is the height known?
Yeah, given height given.
Then you use the
which formula? This one. Initial velocity equal to 0. That's s equal to h. That's all.
Yeah, to find time.
And what is a in this case?
A is the gravity.
Gravitational constant.
Yeah,
9.8.
Is it negative or?
It is negative, but you don't have to consider the sign.
Okay, yeah. You can always like make it positive.
So electromagnetism. Okay, I read the full name here, and this I don't have to. Okay.
Oh yeah.
We got everything. I just highlighted something very important. Can you see? And so this is a Faraday induction law. Can you see? You agree?
Yeah.
This is Newton's second law. Okay.
Yeah.
And this is Kepler's third law.
Yeah.
You see? And anything is important? Important energy. That is very important formula. Okay. And this is just derived. You can if once you know the wavelengths, you can derive this formula. Just remember the harmonica, the lowest harmonica is the longest wavelength. All right. And but the longest wave but is the shortest lowest frequency. Okay. Yeah. I put this formula here. It's useful. Can you see? Okay. You can convert that. Remember.
Longest wavelength.
Yes,
yes,
you can see similar to here. Can you see this increase lambda decrease? Can you see?
Okay.
So that's all based on the formula. But remember, when you're dealing with a photon or light, you have to use C, not V, as we discussed before.
So like if you use into quantum,
this photon electric effect very useful.
Okay.
This is absorption. So this is absorption. This is absorption and energy level. Okay, and this is called Rydberg's formula.
Yeah.
I hope this covers everything.
Yeah,
okay?
basically.
Except the projected motion. We're talking about that. We're talking about how to apply that.
Okay. Let's talk about tomorrow.
Yes.
We'll
okay.
Talk about it tomorrow. Like also vector diagrams.
Okay. I will stop here now. Yeah. All right. I stop now. Okay. See you next time.
Bye bye. Thank you.